Hello everyone. So in today's lesson, we are going to take up time domain analysis with the help of MATLAB. Okay. So let me share my screen. Yeah. So I have already kept my MATLAB open here. Okay. So how will you open that? You will have a MATLAB icon. Double click on that. A new window will pop up. That is what is called the command window. Okay. You can see something blinking here. Okay. So whenever you want to save your programs for future use, you can save them into a new M file by opening a new script file. Okay. So type all the programs in by opening a new script file. Save that new script file into your folder of interest. Okay, so you can save all this blah blah blah, give some name, so store it into your folder of interest by making use of path browser. Okay, so we had seen what is a second order system. Okay, the standard form of a second order system is like this: G of S equals omega n square divided by s square plus 2 zeta omega n s plus omega n square. Okay, what is omega n called? Omega n is called the undamped natural frequency. Omega n is called the undamped natural frequency. Okay, and zeta is called damping ratio. Damping ratio. Okay, so if zeta is equal to 0, then you get an undamped system. Okay, if zeta lies between 0 and 1, you get an underdamped system. Underdamped system. If zeta is equal to 1, it is critically damped. And zeta greater than 1, it is called overdamped. Fine. So depending upon your damping ratio zeta values, the system will display different kind of behaviors. Okay. So let us take a few examples here. Right. Suppose you are given a second order pole, or say you are given second order poles as s is equal to -3 plus minus j7. Okay. You are given a pair of pole pairs -3 plus minus j7. Question is to find what is the damping ratio zeta, natural frequency omega n, settling time Ts, peak time Tp, and percentage overshoot. Okay, so if you remember this thing, where were the pole locations? The second order poles will be at minus zeta omega n plus minus j omega n into root of 1 minus zeta square. Okay, what is settling time Ts? It is given by 4 divided by zeta omega n. And how would you find Tp? Pi divided by omega d, where omega d is omega n into root of 1 minus zeta square. Okay, and how will you find the percentage overshoot? E raised to minus pi zeta divided by root of 1 minus zeta square into 100%. Okay, I hope you remember that, right? So now you need to separate out what is your zeta and what is your omega. Okay, so let's define here P1. My P1 is 1 space 3 plus j7. 3 plus 7 star I. 7 star I. Oh, sorry. Let me open a live script file. Okay, that will be convenient. So you can see what is happening. Clear all CLC, right? So now I will define my P1. P1 equal to 1 space 3 plus 7 star I. Okay, 7 star I. Then P2. What is P2? 1 space 3 minus 7 star I. Okay, so I will put a semicolon also here, or no need. Let it be. So if you run this, what happens? You get what's value of P1, what's value of P2. P1 will be how will you how P1 will be S plus 3 plus J7, and P2 will be S plus 3 minus J7. Oh, there is a mistake here. The minus. Okay. Now what next? We need to find the second order denominator. Okay. So we need to multiply that. Okay. So let me call this as I will give some variable. Okay. Denominator equal to. So I told you in the previous class there's a command called CONP, MATLAB command. It will multiply two polynomials in S domain. Okay. So I can write this as convolution of P1 comma P2. Okay. Then what happens? So you will see the denominator polynomial. Denominator polynomial is 58 plus 6s plus s square. Okay. So keep in mind this 1 plus 6 plus 58 means what? What's the polynomial? Corresponds to s square plus 6s plus 58. Okay. So my omega n square is 58. 2 into zeta into omega n is 6, from which I can find my omega n. Sorry, zeta as what? 6 divided by 2 into root 58. Okay, so that's what we are going to do. Okay, so this is my denominator, right? Now, what will be your omega n? Your omega n, Wn will be what? Square root of sqrt of. So you see, this 58, that is the third term in the polynomial d. Okay, so I can write this as square root of d of 3. Okay, what does it mean? It means that we need to take the square root of the denominator, the third part of the denominator. Okay, the first coefficient is 1, second coefficient is 6, and the third term is 58. Okay, fine. So omega n equal to square root of this thing. So what will you get? Omega n is 7.6158. Okay, omega n is 7.6158. Now, how will you find zeta? So you need to identify zeta will be what? This zeta will be 6 divided by 2 into omega n. Okay, so I can write like this: zeta equals what? So we need to divide the second term. Okay, we need to divide second term. So that means zeta will be equal to what? Denominator second term. Okay, divided by what? 2 into 2 star what? 2 star or 2 star omega n. 2 star omega n. Okay, divided by 2 star omega. One more bracket is required. Fine. So let us run this. Is this correct? Denominator 2, 1, 2. Oh, I think it is extra here. Yeah. Okay. So if you run this, what happens? Your zeta will be 0.3939. Okay. Now, what will be your peak time TP? Peak time TP will be what? That we know, pi divided by pi divided by omega d. Okay. So TP I can write as TP will be what? Pi divided by omega d. What is omega d? Omega n into square root of what is TP? TP we had already seen. TP is, what is TP? Pi by omega n root of 1 minus zeta square. Okay, so omega n into square root of 1 minus zeta square. That will be the peak time. Okay, so it will be 0.4488 seconds. Now, how will you find settling time? Settling time is nothing but 4 divided by zeta omega n. 4 divided by zeta star omega n. Okay, how much is that? 1.333 seconds. But now what next? We are asked to find the percentage overshoot. Okay, so what is percentage overshoot? E raised to minus pi zeta divided by root of 1 minus zeta square into 100%. Okay, so 100% into 100 into exponential e raised to what? E raised to minus pi zeta divided by what? Root of 1 minus zeta square. Okay. Now if you run this, what will you get? Minus pi zeta 26.0176. Okay. Now let us plot this thing. Oh, okay. So, okay. So let us assume that it's a numerator. Okay. So numerator will be say 58. Okay, so let me call numerator. Numerator is 58. Or numerator is yeah, numerator is 58. Okay, so step of num comma dem. So overshoot was 26.0176. Settling time was 1.333. Okay, it's running. You can see here. Yeah. Yeah. So this is the step response. Okay. How to check these things? You can do a right click. Oh, it's not working here. Okay. So what I will do on the what I will do is let me run this in the command window. So now you will get a separate figure window. Okay. So now you can do a right click. What's not working? Right click is done. Okay. Now you can do a right click characteristics. Okay. T response TP. How much was our TP? If you click on the thick solid dot, you get TP as 1.26. Okay. So our TP was, sorry, not TP. So the overshoot was 26.0176%. Okay. So it overshooted 26% beyond the final value. Okay. Then what will be the peak time? Peak time is peak time corresponds to this value. Okay. That will not be displayed. In settling time, how much is the settling time? That will be around 1.11. And what was our value? Settling time as 1.33. Okay, it's matching. Okay, and so on. Right? So in this way, you can find the step response. Okay. Now we have seen different kinds of damping, right? So I will do one thing. We will just compare all the 4 kinds of damp system. Okay. So let me clear everything. Clear space all CLC. Okay. Now let me define numerator as 25. Okay. So let me call my denominator 1 as 1 space 0 space 25. What's the meaning of that? It means that s square plus 0s plus 25. That means s square plus 25. Okay. Then I will call my sys1 as TF of num comma in 1. Okay. So what is that? It means 25 divided by s square plus 25. Why the output is not displayed here? Because I added a semicolon after this command. That is why otherwise it would have displayed sys1 equals 25 by s square plus 25. Okay. Now the command is step of sys1. Okay. Step of sys1. So this command step gives unit step response. Okay. What is this? See, here the time scale is up to 350 seconds. That is why it is appearing too much crowded. Okay. So if you want, you can limit the time. Say, let me define the time. I want to see the plot for 4 seconds only. Okay. Then what you need to do, you need to type step of sys1 comma, you need to define the time period 4. Okay. Now you see what's the output. You will see it is an undamped second response. Okay. Because you see in undamped system, the poles will be on the imaginary axis. Okay. A second order undamped system means there will be a pair of poles on the imaginary axis. So it is giving continuous constant oscillations, which are neither increasing nor decreasing with respect to time t. Okay. And secondly, what is the amplitude here? It is twice. So if you give a unit step input, the output will be oscillating with twice the amplitude of the input signal. Okay, that's the conclusion here, right? So I will hold this for the time being. Okay, so there's a command called hold space on. Okay, so that means it will hold on the figure, right? Because we need to see other damp systems. Now let me come across. Let me take up a critically damped system. Okay, so critically damped system means what? Damping ratio must be equal to 1. So 1 space 10 space 25. Okay, what was the what was the natural frequency here? 5. So 2 into zeta, 2 into 1 into omega n must be equal to is 10. That means 2 into 1 into 5. 2 into 10 into 1 equal to 10. So zeta is equal to 1 here. Okay. Now my second system, sys2. What is that? Sys2 I will call as TF of num comma dim2. Okay. If you want, you can see here. It is nothing but 25 divided by s square plus 10s plus 25. Okay. So now step of sys2 comma the same dimension you have to use. Okay, because then only it will be compatible. Okay, both in the time axis as well as both in the time axis as well as the y coordinate. Okay, so you have to give the same time period. So now you open that figure window. What happens? You can see a red plot. Okay, so this is typically dam system. The red one is a typically dam system. So there are no overshoots, no undershoots. Okay. So since we are already given one hold on, that is enough. If you again type hold on, what happens? It gets hold off actually. Okay. So you need to type hold on only once. Now let us take the third system. 1 space say 4 space 25. Can you tell me what kind of damping will be this? It corresponds to a under dam system. It corresponds to an under dam system. So I will call this 3 as TF of num comma then 3. Okay, and step sys 3. Okay, so if you open the figure window, you will see an under dam response, the yellow color one. Okay, this is an under dam system. And finally, over dam system. Then 4 equal to what? 1 space, say 15 space 25. Okay, sys 4 equals this thing, right? So step of sys 4. Okay, so this plot shows all the cases superposed in the same figure. Okay, the blue one, which is oscillating continuously, is the undamped system. The yellow one, which has an overshoot, that is the underdamped system. The red one, as you can see here, that is the completely damped system, and the maroon one is the overdamped system. Okay, so you can see that of all these performances, completely damped system gives the optimal performance with no overshoots and undershoots. The response is smooth. Okay, this is one way. Or what you can do. So in this case, I had drawn all the figures in the same plot. Or if you want, you can have it in different plots. Say plot 1 here, plot 2 here, plot 3, plot 4. Okay. For that, we need to make use of the command subplot. Okay. So subplot. Okay. So the command is like this: subplot m comma n comma p. Right. That means subplot m comma n means there will be m rows and n columns. Okay, say I am giving subplot 2 comma 2. What does it mean? It means there will be 2 rows and 2 columns in the figure window. Right? P indicates the position. So 1 means the top left, the topmost left. 2 means the top right. 3 means the bottom left. 4 means the bottom right. That's it. Okay. So subplot, right? I have divided it into a 2 by 2 thing. Okay, subplot 2 comma 2 comma 1 comma step of sys 1 comma 4. What does it mean? It means that the figure window is divided into 2 rows and 2 columns. So there will be 4 positions: position 1, position 2, position 3, and position 4. Okay. So what I am doing is that I want to plot my undamped response in the top leftmost position. Okay, that's what I'm doing. So you can see here what is happening. Okay, so this is 2, 2. This is 2 rows, 2 columns. Okay, so I have given here number 1. That's why it is at the top leftmost position. Okay, now subplot. So I want to have the next plot in the top right. Okay, so 2, 2 comma sys 2, the undamped system. So you can see here, sorry, the critically damped system. So this is the critically damped system. Okay, now subplot 3. That means sys 3, that is underdamped system response. Okay, this is the underdamped case. And finally, subplot 2 comma 2 comma 4 sys 4. That will give overdamped response in like this. Okay, this way also you can plot the response. Is that clear? Okay. Now, coming down. So when you gave step of sys comma step of step of sys 1 comma 4, what happened? It gave a response plot like this. Okay, but if you give left side arguments like this, say y comma t equals step of sys 1 comma 4, what happens? You will not get a plot, you will get a set of data points. Okay, there will be two vectors or two arrays. What are they? What are those arrays? One array is y, which contains the y coordinate. One array is t, which contains the x coordinate, the time axis. Okay, you can see here, what is t here? It is increasing. It is increasing. Okay, now we need to make use of the command plot y comma t. Okay, so this will sorry, this is the other way around. Plot x comma y. Okay, so t is the x coordinate, so t comma y. So you will get the step response. Okay, so whenever you use left side arguments, instead of getting a plot, you will get the data points only. Okay, that you should remember. Okay, now how will you find the impulse response? So the command step gave me unit step response. So how will you find the impulse response? Unit impulse response is the command impulse. Okay, so impulse of say sys 3. What was sys 3? Our sys 3 was an underdamped system. Okay, so impulse of sys 3. So that will give you the unit impulse response. Okay, again, as before, if you use left side argument, instead of giving a plot, it will give a set of data points. So then you may have to make use of the command plot to plot between the impulse response and the time. Okay, so to plot a unit step response, we have the command step. To plot a unit impulse response, we have the command step. To plot the unit ramp response, we have the command ramp. No. Okay, you can only plot unit step response and unit impulse response with the help of the commands step and impulse. Okay, so if you want to make any other plot, then there's a command called lsim. Okay, lsim. So what is that lsim? What does it do? Lsim or lsim plot, both are one and the same. Okay, both functions are one and the same. Okay, lsim or lsim plot. Okay, so you can have any response to response to any input with the help of this command lsim or lsim plot. We will take a few examples. Okay, then it will be clear. Suppose you are asked to find the ramp response of say g of s equals 1 divided by s square plus s plus 1. Okay, you are asked to find the ramp response, unit ramp response of this transfer function. Okay, so before I go into that, what's the syntax of this thing? It is like this: lsim sys comma u comma t. That means as the input arguments, you need to feed the time t, the input signal u, and the system. Okay, so let us try this here. So I will remove all these things. Okay, clear space all CLC. Fine. Now what next? We need to define our system. Okay, so num equal to 1 and din equal to what? 1 space 1 space 1. Okay, so sys equals tf of num comma d. We have defined the system. Sys equals tf of num comma d. Okay, so that will define the transfer function 1 divided by s square plus s plus 1. Okay, now if you want to use LSIM plot, there should be three input arguments. One is this, we are defined. Now we need to next define the time. Okay, for what time you need to see the plot. Say 0 is to 0.01 is to say 10 seconds. Okay, so how many time instance will be there? TF minus T initial divided by the increment delta T. Okay, what does it mean? This means that the time starts from 0th instant up to 10 seconds with an increment of 0.01. So how many total time instance will be there? 10 minus 0 divided by 0.01. Okay, so there will be 1000 instance. Okay, so we defined the time variable. Now what next? We need to define the input signal. Okay, what is the input here? It should be a unit ramp. Okay, so how will you define that? U equal to T. Okay, T is a vector. So naturally, u will also be another vector. Okay, so since it's a unit ramp input, we will define u as t. Now what next? lsim sys comma u comma t. Okay, that's it. And run. What will you get? You will get the unit ramp response. Okay, so in this way, you will be able to, find response to any input. Okay, so this was the unit. What is the green color here? Green color is the unit ramp. What is the blue color here? Blue color is the response, the unit corresponding unit ramp response. Okay, why does it find a steady state error? Because what was the type of the system? Type of the system was 0. Okay, so unit ramp to type 0 system will give a constant steady state error. You can see maybe this much is the transient part. 1 to 2 seconds is the transient part, and then on it is the steady state part. Okay, so at steady state it has a finite error. So now suppose you wanted to find the response due to an input due to a ramp of slope 5. What will you do? You just need to type 5 star t. U equals 5 star t and run. Okay, so now you see we have got this. So you see, what is this y coordinate? It is 50. 50 divided by 10. The slope is 5. Okay, so in this way you can find response due to any kind of input signal. Okay, now so this so we have been discussing about transfer functions. So even if your system is in state space form, you can make use of lsim command. Not to worry. Okay, so suppose you are given your A matrix like this. Say your A matrix is given. Okay, A is say -1, 0.5, -1, 0. Okay, your B is a column vector 0 space 1 and C is 1 space 0. Okay, you need to find y of t if the input signal r of t is an exponential e raised to -t. Okay, what is to be done? Again, we need to make use of the command lsim or lsim plot. Both lsim and lsim plot are one and the same. Okay, so we need to define these things. So let me delete this and now define what is ABC. So what is my matrix A? Matrix A is -1 space 0.5 semicolon. Semicolon will indicate that it's the next row. -1 space 0. Okay, -1 space 0.5 semicolon -1 space 0. What is my B? B is nothing but a column vector 0 semicolon 1. Okay, what is C? C is nothing but 1 space 0. Okay, and of course D is not given, so you can take D to be equal to 0. Okay, so we have defined our system. What next? We need to define the time. So what can be T? T will be, say, let us take T starting from 0 with a increment of 0.01 up to 10 seconds. Okay, now what is the input signal here? It is e raised to -t, so exponential of -t. Okay, now what next? lsim sys comma u comma t. That's it. Okay, sorry, not sys, ABCD here. Okay, I forgot that. A comma B comma C comma D. Okay, U and U comma T. Right. So if you run this, this will give you the exponential response due to an exponential decrease in e raised to -t. Okay. So in this way, also you can find the response due to any kind of input. What's the green color line? It is the unit exponentially decreasing signal e raised to -t. What's the blue one? Blue one is the corresponding response. Okay. Let us try another thing. Say, for example, we are asked to find what is the step response. What's the response of this system? 5 divided by s square plus s plus 5 when the input is this is the system given. Okay, when the input is a step input of magnitude 5. Okay, so how to do this? Again, as before, we need to define all the parameters. Okay, so my numerator is 5. Okay, denominator is what? 1 space 5. Okay, then this I am defining as TF of num comma din. Okay, then T again we need to define 0 is to 0.01 is to 10. Okay, now what will be our U here? It's a unit, it is a step input of magnitude 5. Okay, what will be in my U? Any idea? Hmm? Hmm? What will be my U? Is it 1? No. 1 means it's only one single one, right? How many time exponents are here? How many time exponents do we have? We have starting from 0 to 10 with an increment of 0.01. We have minimum 1000 points. Okay, that means we have 1000 x coordinates. Okay, so to plot a point, you need 2 coordinates, x and y. Okay, so if there's x1, there should be y1. If there's x2, there should be y2. Then only you have points, first point, second point. Okay, so like that, there should be 1000 y coordinates. Okay, or in other words, we need to first measure what is the size of the time vector. That many ones have to be generated. Are you getting me? To plot a line, you need minimum 2 points. Okay, say x1, y1, x2, y2. Okay, so here we have the time coordinate. That means the x coordinate we have. How many points? 10 minus 0 by 0.01. That means 1000 points are there. So you have 1000 x coordinates. Where are the corresponding 1000 y coordinates? Then only you can plot x1, y1, x2, y2, x3, y3, etc. up to x 1000, y 1000. Okay, so first you need to measure the size of the vector t. That many ones have to be generated. Okay, unit step. But what's the question? To find the step response when the input is a step of magnitude 5. So 5 into. Okay, so it should be u equal to 5 star ones of size of t. Size of t. Okay, 5 into ones of size of t. Okay, that many y coordinates will be generated. Now what next? LSIM sys comma u comma t. We use the u and t, right? Yeah. Okay, let us run this and see what we are getting. So we got the step response. Okay, so you see the green color, what's the magnitude? It is 5. Okay, and this is the corresponding unit step response. Okay, so with the help of lsim or lsim plot MATLAB command, we can have response due to any kind of input signal. Okay, so that's all about the transition response. Now, how to find stability? So stability, when you solve by hand, you make use of what is called Routh-Hurwitz criterion. Okay, so unfortunately in MATLAB there is no command corresponding to a Routh-Hurwitz procedure. Okay, what you can do is you can look for, there's a command called roots, ROOTS. If you are given a characteristic polynomial, you can check for the roots of the characteristic polynomial. Say for example, you have a quadratic polynomial, say 1 space minus 2 space 4. Okay, so you can make use of the command roots of p. That will tell you which are the roots of the polynomial. Okay, so you see the roots are 1 plus minus j 1.732. Okay, so is it stable or unstable? Is it stable or unstable? It is unstable. Okay, so if you, another method is p-set map of p. Will it work? Let me see. No. So I will call, okay, num equal to say 5. Okay, then sys equals tf of num comma p, right? P is set map of sys. What is that? So you can see here. Okay, 2 indos are here. It is on 1 plus minus j. What is that? Plus minus j 1.732. Okay, it is, you can see here this cross here, right? One is here and one is at this point. Okay, system is unstable. So this is the way in which you can check for stability. Okay, so to check the stability, you need to have the characteristic polynomial, and with the help of the command roots RWTS, you can check the system stability. Okay. So with this, we come to the end of today's session, and we will take up a new lesson in the next class. See you. Bye.